Hey everyone, so today we'll be doing a short demo of a project we worked on called MedIPA. As most of you know, getting access to your medical image that's taken from the hospital is a huge pain right now. MedIPA aims to resolve this problem by providing the necessary tools to allow medical professionals to upload medical images like MRI or CT scans to the internet. This opens the door for a patient to be able to see his own scans as well as consult other doctors for opinions, an online collaboration tool for medical images, so to speak. Aside from rendering images into a 3D model, we allow the user to zoom in, highlight particular color ranges, as well as slicing. As you can see in a little bit, these tools really help the user hone in on important areas very quickly. And last but not least, we allow the user to save current configuration and load them up at a later time.
So the MedIPA system used a wide variety of technologies to achieve both server and the client-side components, which will be covered a little more in-depthly in a review of the architecture. One of the first technologies is a Python library called Simple ITK, which handles processing of the binary medical image scans to be output into a format that is Python readable and then can be manipulated by our own personal code. Other Python libraries that we're utilizing is Flask, which is a micro web framework for prototyping and rapidly building small websites. And we utilize the WSGI server standard as well as the Jinja 2 templating language for our various pages to reduce rewriting the same boilerplate HTML and JavaScript. Also, we're using Celery, which is an asynchronous task queue, to help process some of the I/O and not bog down the user's experience when uploading large image files. On the client side, we're utilizing HTML5, heavy use of JavaScript and WebGL for the rendering, using a JavaScript library that's built on top of jQuery for plotting called Flot, which allows you to quickly and easily build various types of graphs and input data that as well as using, as I said, jQuery and jQuery UI to do a lot of the DOM manipulation and interaction and make that easier, and Less CSS, which is a JavaScript library that lets you write more structured and organized CSS and reuse the CSS that you've written for more rapid building of the site. So next I'm going to go over a little bit, give an idea of what the architecture behind all of this is like. So user opens their browser, connects to the website, and all requests are processed through a thin Flask layer, which has a URL mapped to a function in a one-to-one relationship, and based on whatever that particular URL is intended for, that view will handle different attributes in regards to manipulating the data. And so it does that by going through a small image handler library that we wrote. So that image handler library does a couple of things. It handles manipulation of the data as well as calls out to the simple ITK library to handle and process the image files. And we are using a simple data store, just the file system, and storing the PNGs and JSON files that we generate down to the file system itself. And we're using a crude version of a NoSQL database in that we store a kind of JSON file on disk that contains properties and locations of files and file names for accessing, as well as saving some configuration and user-defined data that we'll get into a little more later. That image handler library also will, whenever a file is uploaded, handle the making calls to the asynchronous task queue that we've established with Celery. So anytime a request, an upload of an image file comes in, the Flask layer hands it off to the image library as a task, or sorry, sends it off as a task which is entered into Celery. Celery puts that task into its task queue, which is the underlying task queue is RabbitMQ. And Celery handles managing when those tasks need to be processed and when there are resources available and keeping track of them, and makes calls to the image library to process the file and save down data to the file system. And once that's complete, those images will be available to the front end UI that the user will access by hitting URLs that Flask is handling for us.
Moving on to rendering algorithms, we use two-pass raycasting. The first step is to rasterize to find the starting point and the direction of the ray, and the second step is to calculate the color and opacity, knowing the starting point and direction for each pixel, and draw the results on the shader. With the first step, it is possible to use a bounding box surrounding the volume and finding the intersection between the ray and the bounding box. But in order to improve time performance, we use the two-pass raycasting. The front face texture provides the start position of the ray, and the result of subtracting from back to front face texture provides the direction of the ray. Now going on to the next step, knowing the starting point and the direction, we can calculate the color and opacity for each pixel. The rays are shoot from each pixel position through the volume and samples along the path by equal intervals. As the sampling points are advanced along the ray, it accumulates the opacity and color values of the sampling points. The process is optimized by stopping when the accumulated opacity reaches to the maximum value, which is 1, or when the advanced steps reaches to the length of the ray. Below is the composition equation that we used for front to back composition, and this computation is done in parallel for each ray, and the results are sent to the shader. The advantages of raycasting is, as mentioned before, it enables empty space skipping, and it does not depend on the projection view, and it enables parallel processing by computing for each pixel, for each ray.
So this is the landing page you arrive at when you access the MedIPA site, which we have running here on an Amazon EC2 cloud system. It just basically gives you a list of the images that have currently been uploaded, and allows you to select between viewing this list and uploading. So if we go to the upload page, you can see it allows you to upload a file directly from your file system, or specify a URL that could be that points to an image file. And once you hit the upload button, a background process kicks off, which converts the image to a PNG image file and allows for a lossless compression, which reduces the size of the image and gives a better user experience because the user doesn't have to wait as long. It also reduces the images to different levels, so it's sort of an 8 times reduction, a 64 times reduction, and a 512 times reduction. And so this allows the image to be almost instantly displayed to the user, and then we can increase the resolution the longer the user is at the site. So next we'll show you what an image looks like when it is rendered. We'll first go to the head image that we have here. And so the first thing you'll notice when you arrive is the little auto slider up at the top which adjusts the quality. By default, we start with the lowest resolution image, load that and start rendering it, and then get an estimation of the user's frames per second. If it's above a threshold, which we currently have at 10 frames per second, we then increase the quality, download a new image, and try to render that. And we just keep doing this process until we're actually rendering the full image. And at any time, you could disable the auto adjustment, or if you just wanted to reduce it or increase it to push your system a little bit more, you could. And this all happens in real time. So for example, here's the 512 reduction, and then as we scroll up, it goes up to the highest. And the image allows for basic rotation along the X and Y axis, and zooming with the mouse wheel in and out. And generally on a fairly fast system, this happens at a pretty decent frame rate, anywhere from 30 frames per second to 100 frames per second. We also have brightness and opacity controls, which allow you to, as they sound, adjust the brightness and opacity of the image. Depending on the image, you may have to adjust things differently. Also, when we get into cutting, you'll see that adjusting the brightness is very important. Next, we move on to the histogram that we've generated. This is a plot of the number of pixels that have particular values. So on this image, we see that the values go from 0 to 256, which is an 8-bit grayscale image. And then the number of pixels are plotted along the y-axis here. And this is to help the user to highlight or to be able to identify different aspects of the image that they can hopefully highlight. And depending on the different image or the different thing being represented, can have a drastic effect on the usefulness of this histogram. But so for example, if you just highlight on the list, you'll see it instantly light up. The histogram itself is rendered using the JavaScript library float, and so we're just passing the data values down to the browser. And then it also allows you to zoom in, so you can select something on the histogram and then zoom. So if I wanted to really narrow down what I was trying to highlight, I could use that. And you can adjust the color of the highlight by opening a little color picker here, where we can adjust the color that we want, and then also the alpha channel. So we can make it more or less sort of translucent. And I'll hit OK, and the color gets applied. Now, highlighting one selection is good, but we a lot of times want to be able to highlight multiple things. And so we can actually save that highlight to a list. And so this allows us to highlight another region. Let me pick a different color. So as you can see, we can highlight multiple items, and basically this list that we have here works it's an ordered list, so that things at the top of the list take priority. So for example, currently I'm highlighting these different ranges at these colors, but if I picked a similar range, so for example the blue goes from 51 to 65, if I highlight that range again, which is just an estimate, and this time I'll pick, say, purple. And I'll get rid of the red just for now. And then I'll save that as a highlight. As you see, the purple seems to have overtaken the blue simply because it's overlapping the blue in a lot of places. We can sort the list manually, and now the parts that were overlapping with the purple have now been actually highlighted blue again. And as you saw before, I can remove a different highlight if I want. And since this also allows for the alpha channel to be selected, it means we can hide things. So for example, I'll highlight the majority of the head, and if I set it to an alpha 0, it basically disappears. And you can play with each color sort of before you actually save it to the list.
As you can see from the model, if I tweak the control just a little bit on this axis, the top of the brain starts to slice off. This is basically the functionality of slicing. We allow the user to be able to cut off certain pieces of the model and thus allowing them to examine the parts that they want to examine without all the clutter. As you can see from this angle, we basically can cut the brain off into a tiny little cube. This way, if we really wanted to, we can simply examine this slice and highlight and annotate however we want.
So now we've shown you all of the different controls that we present for you to use for viewing these images. But it wouldn't be all that useful if you had to go in and reset up an image the same way every time. So we've added this concept of configurations where you can save the current state. So we'll save it as purple. And you can add a comment to it to sort of if you wanted to explain what you're highlighting. And then we can just save that configuration. And then loading configuration is as easy as just hitting the load button. So here, for example, we've got the same brain. It's just highlighted and zoomed and sliced to highlight something interesting. And if we wanted to switch back to the one before, we could just load that. And just in the same way, load the default image. So this really allows you to point out things that are interesting and saves a lot of time if you're going back in. And we, similar to saving, we allow you to delete. So we'll just delete that one I just created. And lastly, the full screen just simply allows you to view the image in full screen. If you don't really want the controls, you just kind of want to examine what you highlighted. The other image we have to view today is of a liver scan, and I'll show you that real quick. And this is sort of what I was talking about. The liver is much dimmer, so we need to increase the brightness a bit just so that we can see. And this is especially a good example where you really can't tell what's going on in this thing without highlighting. So we've got some predefined configurations that are sort of neat. So this is, you can sort of see the kidneys and other structures, but even more so, here we can clearly identify the kidneys, the two kidneys that are available, and you can see stark contrast on the different structures. And then one last, this sort of shows a zoomed in view of the cavities of the kidneys. And this is actually a fairly thin slice where we're actually slicing into the kidney, and you can sort of see these little pockets. If I was a doctor, I might could tell you what those were, but I am not.
Thanks for watching, and if you have any comments or questions, or you'd like to take the source code on a test drive for yourself, please go to the link we've supplied in front of you, github.com/ehelm/medipa_web, where you will find instructions on how to fork the repo, clone the repo, and install it, and the system requirements.